Okay, so in the last lectures we have been talking about free vibrations. Okay, we have seen that vibration can be um, undamped or it can be damped. Okay, and we have seen in the last lectures that in undamped free vibration, sustained, steady, periodic oscillations exist. Okay, so the system will undergo periodic oscillations, and the amplitude of the oscillation stays constant throughout the period of throughout the entire vibration cycle. Okay, but in the damped case there is a viscous dissipation mechanism present, so it will make sure that there is no motion after some time. Okay, so this is what we have discussed in the last class, and you see that here this is simple physics. The physics is very simple. Okay, and there is no complex mechanisms present in free vibrations. Okay, however, most are in reality all engineering systems are subjected to forced vibrations. Okay, so all engineering systems are subjected to forced vibrations. Okay, by forced we mean external forces act on the system. Okay, so this is what we are going to discuss in today's class. We are going to talk about forced vibration and resonance. Okay, so this is what we are going to discuss in today's lecture. Okay, again, you know that the system will be concentrating on is a spring mass dashpot system subjected to external force. F of t. Okay, so we have a spring of stiffness K and a dashpot represented by C attached with a mass M, but now it is not but it is subjected to external forces given by F of t. Okay, so the governing equation you can very easily write in a straightforward way. The governing equation of the system is mx double dot plus cx dot plus kx is equal to 0 for a free vibration. Now that becomes f of t. Okay, so that is an equation for a governing equation for forced vibration. Okay, and f of t is equal to 0 implies free vibrations. Okay, that is very obvious. Okay, so now we consider forcing f of t to be, we consider f of t of the form f sine lambda f t. Okay, where capital F notes the magnitude of the force and lambda f denotes the frequency of the applied forcing. Okay, you know that the reason for choosing this function is that any function or any complex function can be written in terms of sines and cosines. Okay, and that is Fourier series. Okay, I don't know if Fourier series has already been taught to you. Maybe it's there in the next semester. So using Fourier series, we can write any general function as a combination of sines and cosines. So what we derive in today's class is not just restricted to this one function, but using this result, you will be able to represent any function. Okay, so you don't really have to know Fourier series at this point, because we are not going to use it. Okay, it is just to show that the derivation that is going to be happening in this class is not just restricted to this function alone. Okay, it can be used for a general forcing function. Okay, only that much you have to know. So equation A, the governing equation A, is a non-homogeneous ordinary differential equation. Okay, and you must be knowing that the solution x of t will have two parts. One is the complementary function, plus a particular solution. Okay, you know this already, right, from your ODE course. So complementary function can be obtained by solving the corresponding homogeneous equation. Kx plus Cx dot is 0, and which we did already in the last lecture. Okay, so the complementary function we already know, so we will not bother about this, and we are going to be, in this lecture, we are going to be concerned about particular solution. So we derive this now. We are going to derive the particular solution for this non-homogeneous ODE now. Okay, we can assume that, the particular solution let's say x part of t is of the following form, right? So we can write this as xm, which represents the magnitude of the oscillations sine lambda ft minus phi. Okay, so how can we write it this way? Okay, so the reason for writing the function like this is that the body or the system is subjected to sinusoidal forcing. Okay, so it is natural to assume that the body will undergo sinusoidal oscillations. Okay, right, so we have now two unknowns here. So this is magnitude of the oscillation, this is the phase lag between the applied force and displacement. Okay, so we have two unknowns which we have to find. Okay, how do we find these two unknowns? Any idea? Right, So we substitute this equation 1. So to find the unknowns, we substitute equation 1 in the governing equation A, which is given here. Okay, so we are going to substitute the particular solution in governing equation A. So what you would get is minus xm times the mass lambda f square sine lambda f t minus phi plus c xm lambda f cosine of lambda f t minus phi, okay, plus k xm sine of lambda f t minus phi is given by f sine lambda f t, the applied forcing. Okay, so now we make, okay, so lambda f t minus phi to be 0. Okay, so in this case the both the sine terms get cancelled, and what we get is c xm lambda f is equal to f sine phi. Okay, let us say this is equation 2. Then you make lambda f t minus phi is equal to pi by 2. Okay, so in that case all the cosine terms go to 0 and the sine becomes 1. So what you get is k x m minus xm times m lambda f square equals f cosine phi. Okay, so we have two equations and two unknowns. Okay, as you know that the unknowns are the amplitude of the oscillations and the phase phi. Okay, so we can, from these two equations we can find these two unknowns. So in order to do that, what do we do is to take equation 2 square plus equation 3 square. Okay, so what you get is c lambda f square plus k minus m lambda f square the whole square times xm square is f. Okay, so from here you can write in a straightforward the amplitude of oscillations f to be f by, so this is f square, sorry. Okay, so f by square root of c lambda f square plus k minus m lambda f square. Okay, so xm gives the amplitude of the oscillations, and we have another unknown phi, which is the phase lag between the force and the oscillation. We can get directly by dividing equation 2 by 3. It will directly give you tan phi is c lambda f by k minus m lambda f square. Okay, so now we can completely describe the particular solution, because there are two unknowns, magnitude and the phase lag. We found them both. Okay, so what we are going to do is to rewrite these quantities in a different way. So we are going to introduce few quantities. Okay, so you know that, so we know that the natural frequency of the system lambda n is square root of k by m. Okay, and the critical damping frequency, or the critical damping coefficient, sorry, C subscript C, what we have seen in the last classes is 2 square root of km. You can refer to the previous class lecture to see this, and then this can be written as 2m lambda n. Okay, so let us say this represent equation B. Okay, so in order to study the forced vibration, we introduce another quantity called magnification factor. Okay, so we introduce another quantity called magnification factor, which is G, which is denoted as G, which is given by amplitude of the forced vibration divided by static deflection due to F. Okay, so by static deflection due to F, what we mean is that we consider the spring mass dashpot system. Okay, instead of a periodic force, we apply a constant force F here. Okay, so due to this force F, the mass will deflect by an amount x. So the mass will move here due to the force, and by equilibrium you can get x equals F by k. Okay, that is the static deflection due to F. Okay, so that is static deflection due to F. So the magnification factor can be written as G is the amplitude of forced vibration is xm, static deflection due to F is F by k. Okay, right. Okay, so let us say we have given this to be B. Okay, we should have given this to be B, and let's say this is C. Okay, so using B and C, and after doing a little bit of algebraic manipulations, we can get, so using B and C. Okay, you can write the magnification factor G to be 1 by 1 minus lambda F by lambda n square whole square plus 2 C by Cc and lambda F by lambda n. Okay, there is a square root here. Okay, and tan phi 2 lambda F by lambda n by 1 minus Okay, so the amplification factor, magnification factor, and the phase can be written by using these two parameters given by frequency ratio. Okay, so here where frequency ratio lambda f by lambda n, which is the frequency of the oscillating force to the natural frequency of the system, and the damping factor C over Cc, where Cc is the critical damping coefficient. Okay, so now to study structure sensitivity to oscillatory loads, we can use frequency response curve. Okay, so the structure's sensitivity to oscillatory loads is given by frequency response curve. Okay, so frequency response curve is the curve between magnification factor G against the frequency ratio. Okay, so which is lambda f by lambda n. So let us say this is 0.5, 1, 1.5, 2, etc. Okay, here we say this is 1, 2, 3. Okay, so when lambda f by lambda n is 0, you will see that G will always be 1. Okay, and then the curve goes like this. Okay, if it's not going to be 0, so this is going to be C by Cc is 1. Okay, so let me choose another color. Okay, but when C by Cc is 0.25, we are going to get something like this. Okay, there is a C by Cc is 0.25. So there is a peak observed at lambda f by lambda n is 1. Okay, you see that when you decrease C by Cc, okay, it's going to be like this for okay, so this is for C by Cc is 0.125. so when that quantity goes to 0, when there is no damping present in the system, what you get is that this is going to be infinite. So this is C over Cc is 0, which implies G is infinity. You can see from this equation, when lambda f by lambda n is 1 and C by Cc is 0, this quantity is 0, so G tends to infinity. Okay, so what does this mean? Okay, so you know this already. This is what so this is what do we call as resonance. Okay, it means that when when frequency of forcing lambda f and natural frequency of the system lambda n are equal, okay, then the oscillatory motions will have infinite amplitude. And we call this condition as resonance, which you must be knowing from your high school physics. Okay, you can check that we are getting infinite displacement by from this equation. Okay, so we haven't actually done this, so you do this on your own. So do the derivation of this on your own. Okay, this is very simple. It will take I don't know, maybe 15 minutes, but it is very simple and very straightforward steps. Okay, so you know what resonance is now. Now we will stop this lecture by this one discussion: is resonance good or bad? Okay, so it's not good. For example, they are undesirable in any machinery. Okay, because they lead to large stresses in the structure, and it also leads to undesirable motions. Okay, and even unpleasant sounds. So for example, a building resonating with earthquake vibrations is more likely to fall. Okay, if the frequency of the earthquake vibration and the natural frequency of the building becomes equal, the building is more likely to fall, or it's going to fall most of the time. Okay, so but it is good in some sense. For example, you must be knowing about MRI, which is magnetic resonance imaging, which is used in medical diagnosis now. Okay, you can check how this is working. Okay, check on your own how this works. Okay, and your musical instruments uses the concept of resonance to make clear pitch sounds. Okay, and also in microsensors, in order to amplify signals, resonance is used quite often. Okay, thanks. I'll stop with this. We are done with the theory part of the course. I will send few more tutorial parts and then we'll stop. Okay, thank you.